Okay, the lecture is recorded. Thank you for Akhil who are reminding me. I would then continue. As you remember, we're gonna have a makeup exam or assignment rather. It's not gonna be exam. It's gonna be an assignment, makeup assignment for those who missed points. And considering that this is a great week for many individuals, and next weekend is Easter, and many of you may want to be with your families and celebrate it. I was planning, therefore, I plan to give this makeup assignment, not this week, but the next week. But again, what I would like you to do, and I would like you to do it between tomorrow, starting tomorrow morning, and Wednesday evening, on Tuesday and Wednesday, between tomorrow morning and Wednesday evening. I would like you to send me emails of those who want to take it. On your email, and I will send you an email and an announcement for that. On your email, I would like you to tell me how many points you want to capture that you missed and why you missed those points. These two things. Don't write very extensive descriptions, just those two things, so I know how to construct the makeup assignment. I will also send you an announcement for that. All right. The next thing that I now would like to do is to start the lecture for today. And I understand that I got some very good feedback from a few of you about the material on transmission lines, that we need more examples, which I knew already, and that so far we have talked a lot about formulations, which we have to do, and you will see from the examples that we started last week, but we will start more solving today, that those formulations are extremely important for solving problems. We could not solve problems without having those formulations. So we'll start today. I also wanted to start with a few definitions that I believe will be important for us. We have talked about them, but I wanted to put them down in writing so we all talk about the same thing. So I will start with operating frequency. Operating frequency is the frequency of the source. We will always need to remember that. When I say the operating frequency is F, it means the frequency of the source. Second, the free space wavelength. Now, you probably remember from your physics classes that your free space wavelength here, lambda naught, we indicate as lambda naught, is nothing else but the velocity of light in free space, c sub naught, divided by the operating frequency. And we have that c sub naught is given by this expression, 1/square root of epsilon mu, epsilon naught mu naught, and in free space is 310 times 10 to the 8 meters per second. So if you apply this formula here, you're gonna find that the wavelength in free space for an operating frequency of 1 gigahertz is equal to 30 centimeters. Okay, so this is important to remember. So free space wavelength lambda naught, for all of the transmission lines that we will solve in this semester, we will assume that we have an operating frequency F from the source and a free space wavelength lambda naught. Now, I will not always show it as lambda naught, I will show it as lambda, but it is in the wavelength in free space. Okay, now we go to the regular wavelength, which generally is the wavelength that characterizes whatever transmission line we have. If it's a microstrip, it's going to be a particular wavelength for the microstrip. If it's a coaxial waveguide, it's going to be for the coaxial waveguide, and so forth. So we are now talking about real transmission lines, practical transmission lines. That wavelength here is equal to C, which is the velocity of light in the dielectric that separates the conductors of the transmission line. So in the coaxial waveguide, whatever dielectric you have between the inner conductor and the outer conductor. And in the microstrip, whatever effective dielectric you have. You remember that we go from a infinite dielectric that separates the upper conductor for its ground. And then when to go from that microstrip to an ideal parallel plate waveguide, then we replace epsilon by an epsilon effective. As you remember when we started talking about, it was during the introduction to ideal transmission lines. So this epsilon that you see here is whatever epsilon is either the dielectric, if it's fully covering, filling the space between the two conductors, like in a coaxial waveguide, or the epsilon effective, like in a microstrip line. It's going to be given by the designer, and we have not learned how to calculate it ourselves, with the exception of microstrip line. So this is only to inform you that the velocity of light in such a medium is equal to the velocity of light in free space divided by the square root of the relative dielectric constant and the relative magnetic constant here. However, as I said before, for everything that we will do in this class about ideal transmission lines, we'll assume that this C is nothing else but C naught, as I told you up here. Okay. However, I wanted to introduce the concept of the wavelength so you know exactly how we use it and what it means. Now, also in ideal transmission lines, you will see us talking about two different types of lengths. One is the electrical length, and we will talk about lengths D1, D0, D sub S, whatever, different lengths of the different sections of lines. Most of the time, we're talking about the electric length, and the electric length of any section of line is nothing else but the length given in terms of the wavelength, lambda. For us, it's going to be lambda naught, obviously. So when I ask you to find the length of the line, a lot of times I don't want you to find it in centimeters or millimeters, but I want you to find it in wavelengths. If I want you to go further than that and find it in a metric system, I will let you know. And in this case, I will talk about the physical length. So the physical length is defined in the length as the length of the line in centimeters, meters, or whatever. And to be able to find the physical length, you have to calculate lambda, obviously. So we have two different types of lengths: the electrical length that is expressed in lambda, and the physical length, which is expressed in the metric system in the units of length. And that will only calculate if I ask you to do this, which implies that you will have to calculate lambda. Okay, I would like to stop at this point and ask you if you have any questions about those definitions. Do you have any questions? I don't see anything as question listed here. So we are going to move to the next. Also, definition, and then we'll start solving problems. Okay. We have talked about a type of a transmission line circuit that we call a stub. And a stub is nothing else but a section of line that is either open at the end or shorted. So it's either an open end or a short-circuited section of a transmission line. And those, we use them to do matching on transmission lines. And I have here two possible configurations, this one and this one. Now, you have the opportunity for either configuration to either represent it in terms of impedances, like here, where everything is represented as an impedance. So the characteristic impedance of the line is as an impedance, obviously. This is what we call a series stub because it's connected along the conductor of the line, as you can say, so in series on the conductor, and is represented by an impedance, which is called the stub impedance, Z sub S. This one is another configuration that shows a stub that is connected in parallel. And for this one, I have used the admittance type of characterization, where everything from characteristic admittances, the characteristic admittance is the inverse of a characteristic impedance, as you can imagine. So a characteristic admittance is to an admittance at the input of the stub. And then you see that we have this kind of equivalent characterization then when the stub is connected in parallel and is represented by an admittance. You can also here represent everything in terms of an impedance, as you will see later. You can also here represent everything in terms of an admittance. What you should not do, so you don't get confused, is to have half of them represented here. So characteristic impedances, but then admittance. Characteristic admittances, but then impedance. Now, it's not like incorrect, but if you do it very early without being experienced, then you're going to make a mistake. That's why I'm suggesting to try to simplify things as much as possible. If you have to mix impedances and admittances, you always have to remember that you will have to be careful when you write the expressions, all right, the various expressions. So, any questions about this topic, this introduction? There is one question here, and let me just 1 second. Say, why do we distinguish between the two? You're talking about distinguishing between the series or the shunt configuration, or distinguishing between impedances and admittances? Could you write one more sentence so I know? Impedance and admittance. Okay. For the following reason, the expressions, so for example, as you will see later, to find the input impedance Z sub S here for this stub, I use one expression. To find the input admittance for the same stub, I will have to use a different expression. So if you have not been very experienced and you use everywhere impedances, and then you want to write admittance, but you use the impedance expression, then you're going to make a mistake. That's what I'm saying. It's not, I want just to make you aware that if you start mixing, as you may have to, as you will see in an example much later, but if you have to start mixing impedances and admittances, be careful and try to select the right expressions. the expressions for the impedances when you use impedances, the expression for the admittances when you use admittances. That's why I'm saying. That's why I'm trying to differentiate. It's a very innocent but very common mistake that people make, especially early when we do transmission lines. Okay. Now we move down and we are going to talk about this transmission line, and I will start writing now at this point because I have these notes, my notes that I put together, because I know that there are limited examples in the textbook and there are limited examples on the web. For some reason, a lot of this material is included in microwave circuits books, and you find it sprinkled here and there. So I'm gonna give you my notes from this point on, and I will ask you to read my notes first and then read the book or anything else. Okay, so here, I would like to see if I get a stub, and in this particular case, the stub is open-ended. How do I represent the stub as an impedance? So if I look at the stub here to your left, let me see. If I look at this stub here, all right, so obviously I would like to, if the input admittance to this open circuited stub is this abyss, I would like to get rid of the stub, which makes my whole structure multidimensional, and replace the stub with an impedance. In this particular case, you see I have Z naught, Z naught, so I would like to replace it with an impedance. In that case, I will go here and place, oops, sorry. I have to do this again. And as a matter of fact, I will have to do this now that I erased it. Okay, I will have to replace this stub at the points C and C prime with an admittance. Is this a base? And before I do anything else on this configuration in this circuit, I will have to write an expression for the impedance, or the is this a base, which represents the stub. So we have to represent it by an impedance is a base as a shunt configuration. Now, forget about the blue line and for a moment, forget about the blue line and look at what we have here, which is the stub. In this case, what you see is practically an open circuited transmission line like this that has a characteristic impedance, Z naught in this particular case, and is open-end here and has a length this abyss. All right, and I would like to find here the input impedance, this abyss, and these are points C and C prime, and this is the end D and D prime, and this is open-end, open circuit, I would call it, rather. Now, the expression for the input impedance here, this abyss, is equal to Z naught, and then I have ZL, which are, in our case is an open-end, plus J Z naught tangent of beta ds divided by Z naught plus J ZL tangent of beta ds. And ZL goes to infinity, yes, which is the load, ZL, because ZL is the open circuit. Now, if that happens, then this abyss becomes, this goes to infinity, so this term is much larger than this one. So this term here is much larger than this one. And this term here is much larger than Z naught. So that gives us a minus J cotangent of beta ds. All right, so Zs here will be times Z naught, will be J Z naught cotangent beta ds. And if you have Z naught here, and you have beta, which is 2 pi over lambda, and you have ds, then you know exactly what your Z sub s is. All right. If now I will erase this one, and I will put here a short. Let's assume this is shorted at the end. The impedance here, the expression remains the same, but this changes. So the expression here tells us that Zs is equal to that. Now your ZL is 0, since it's a short, and since it's 0, Zs then becomes J Z naught tangent of beta ds, and there is okay, ds is the name of the length, you're right. I call that ds because a lot of times we are gonna call this distance d, say for example 1, we'll call this distance d0, and so forth. We give it different names. And I call this distance d sub s, so you remember that is the length of a stub. Okay, and therefore you can replace the stub by this shunt impedance, but now the value of this is going to be J Z naught tangent of beta ds. Okay, so you have these two separate expressions for open end, open circuit, and short circuit. All right, any questions on this? All right, let me see questions. Okay. Now, let's move down to doing, you remember I told you that we can do the same thing in admittance representation, admittance as we call it form. Okay, now you will see why we wanted to be here careful so we don't mix in admittances and impedances, just, and even if we have to mix them, be careful, be aware of their differences. So here we are looking at the same stub, and this is C, the stub is like this, and we'll keep it open, open end, open circuit. In the beginning, this is Y naught, and we are looking here and we see a YS. And the expression for this YS is coming out of the following expression for any input impedance, or excuse me, input admittance in terms of the characteristic admittance of the line and the load, which is also in an admittance form. It's identical with impedance, but everything are in admittance forms. So if you have any load at the end of a section like this, then the input admittance at CC prime, if you have any load here, like this, will be this one. It's very similar to what we used for the impedance, but everything is in an admittance form, like this. Okay, now let's assume that Y sub L is an open circuit. What is the value of Y sub L when it's an open circuit? Remember the value of Z sub L when it's an open circuit. Let me write it here. So open circuit. We know that the load of an open circuit is infinite as a resistance. So what does that make Y sub L, which is the inverse of Z sub L? It makes it 0. Okay? If that makes it 0, that Y input, in this case, which is Y sub S for us, for the stub, it will be equal to Y sub L is 0, so it's going to be Yj, Y naught, tangent of beta ds. Okay? So for an open circuit, if we put here Y sub S to represent the stub, this Y sub S will have to be J Y naught tangent of beta ds. And this is for an open circuit. For open circuit. Now, if we go here and write this as a, create this as a short circuit at the end. So now for a short circuit, we'll have that Z sub L, we know in the short circuit is 0, all right? So your impedance at the short circuit, the resistance at the end is 0, which makes the equivalent admittance, which is the inverse, all right, of ZL, will make it infinite. And in this case, from the above formula, if YL is infinite, this term here, is much larger than Y naught, and this term here is much larger than this one, which makes it minus J Y naught tangent of beta ds. Okay, so Ys in this case will be minus J Y naught cotangent. I always cotangent. Beta ds. And that will be short circuit. All right, so now we know how to represent a short-circuited stub, both for a in the impedance form as well as in the admittance form. Pay attention, however, to how to find the expressions for an open circuit and a short circuit. The expressions are different when you go to an impedance form or when you go to an admittance form here. Any questions at this point? Yes, always y should be defined as 1 over z. Always admittances are defined as 1 over z, okay? So you need to remember that. And of course, if it's a characteristic admittance, it's gonna be 1 over z naught. If it's an input admittance, it's gonna be y input equals to 1 over z input and so forth. Is 1 over whatever is the corresponding impedance. Now, the same thing we can do, and I will be very brief in this one. The same thing we can do for a series stub. So in a series stub, if we have this line as the expression that I show you here on the left, we look at this one, then that is going to be equivalent to a line here. That's A prime. Here at the center, make it a little bigger, will be C and C prime, and here B and B prime. And here we are going to place a shunt now, excuse me, a series load. Make it this one. I want to have a little bit of space. Okay. And here we are going to have a series load like this. And that will be Z sub S in this case. Or we will represent it, as we will see later, with a same series connection, but it's going to be a Y sub S if we want to. If we choose to go with the Z sub S configuration, so Z naught here and Z naught here, and this is C, all right, in one place. And this is C naught. And this is C naught here. Then that is going to be a common ground for C and C naught. All right. So I would just leave it as like whatever point was here before. And then so instead of the stub, we have a series impedance, where now Z sub S, it will be J Z naught tangent of beta D sub S when the circuit is a short at the end, and Z sub S will be a minus J Z naught cotangent of beta D sub S if it's an open circuit. All right, so also if we want to do it in a admittance form, we are gonna also have a similar configuration as above, with A here, A prime, C here, C prime, B here and B prime, and this is there. And here we're going to have a Y sub S, and then we'll have Y here, naught, and Y naught. And in this particular case, Y sub S will be minus J Y naught cotangent of beta D sub S if it's a short circuit, and Y sub S will be J y naught tangent of beta ds if it's an open circuit. And these are all of the possible configurations we can see of stubs. Now, I'm going to move to a problem, but I would like to see if you have any questions. Maybe you can ask me questions while I'm solving the problem. And it's going to be similar to whatever problems we are going to solve from now on in this class. So here, let me see, I'll solve examples. Okay, we'll solve this problem here. The problem says the following. We have a circuit, which is like this. And we have an impedance at the end of this circuit, a load, which is 100 ohms. And so now we are designing circuits, all right? We have a load of 100 ohms. We have a voltage source here, V sub S. We have a voltage source that V sub S. We have a Z sub S naught, which is 50 ohms. And you can see this from down here. I give it to you. So the characteristic impedance of the line and the source impedance are the same, and they're 50 ohms. 50 ohms here, 50 ohms there, 50 ohms here. But this one is 100 ohms. And if you just leave the line without anything, then the input impedance here is going to be different than ZS naught. And if you remember, we said that for optimum transfer of power from source to the load, you need to have ZL at A prime. In other words, whatever impedance you see right here, if you look towards the line, this has to be equal to Z sub S 0 complex conjugate, which means 50 ohms. All right, this is a very important relationship that you have seen in circuits, you have seen in physics, and we will remember it again here. We're not, the book has a proof of this, but I don't want to prove it again. You're just gonna have to remember it. Since Z sub S 0 is 50 ohms, so Z sub L AA prime, which is the impedance you see right here, has to be 50 ohms. But if I do nothing, and I leave the impedance the way it is, then I will see something other than 50 ohms. So now as a designer, I have, as we say, I have to match this line to the source. So I have to do something here to be able to see an input impedance here, which is 50 ohms. That's a design problem, as we say. Okay, so here is how I articulate that. I tell you to find D1 and DS so that the reflection coefficient right here is 0, which means I want you to find a stub which is short-circuited, place it at an appropriate location, D1, so that gamma at points C and C prime as we look towards the load is 0. If the gamma is 0 here, then what we know, and since we know that the magnitude of this gamma will be the same along this line from that point to the left, then reflection is going to be here, 0, which means that if this input impedance at this point is going to be equal to the characteristic impedance of this line, which is 50 ohms. So if I make gamma 0 here, then is 0 everywhere else, and then my impedance here is going to be 50 ohms. That's how I'm thinking. Okay, I don't want you to think that way. I'm just asking you here to find those. And then practically, I'm asking you to prove in number 2 that ZLAA prime is indeed 50 ohms. That's what you have to do. So now let's try to solve the problem. First of all, I have given you impedances everywhere. So my initial thought is let's use an impedance representation for the stub. And the stub is connected in parallel and it's short-circuited at the end. So on the basis of what we discussed, this base will be equal to J Z naught tangent beta this base. All right? From this. This base is this length, Z naught here. This base is what you see inside the stub. So we are going to replace the stub with this impedance. Perfect. So now that we know. Then we cannot do anything. We cannot find Z sub L at BB prime because that's what we need to find gamma. So gamma at B prime is nothing else but Z sub L, which is the total impedance as we see towards the load at BB prime minus Z naught over V sub L BB prime plus Z naught. So in order to find this gamma, I'm asking you, in fact, I have C there. Okay, let me just make some, for some reason I put C. I have to correct that. B, C here, C prime, B here, B prime. And then, so C, C prime. All right, to be able to find this, I need therefore to have C, C prime here, okay? C, C prime. All right, so we need to find ZL of C, C prime. What is ZL of C, C prime? ZL of C, C prime is nothing else but the parallel combination of Z sub S with Z input and C, C prime. Z input at C, C prime. Okay, so we need that. We need this to be able, we need 2 to be able to find 1. Now, how much is Z input at CC prime from the formula that we have? From the formula we have, which is Z naught ZL plus J Z naught tangent of beta D1, which is this length of the line from C to B, D1. And then we have Z naught plus J ZL tangent of beta D1. All right, this gives us the input impedance and C prime. Okay, so if we have these two, practically we can find the parallel combination of the two impedances, Z sub S, which I have here. All right, and Z sub in CC prime. I, at this point, will try to reduce the complexity of the formulas by normalizing. You remember last time we said if we have the same characteristic impedance, if we have same characteristic impedance everywhere, we can normalize with respect to that in the circuit. So now we can write the following. We can write all of the impedances as normalized. So ZS I can normalize with respect to Z naught, and it's going to make J tangent B ds. I can then have Z input at CC prime to be normalized, which then is going to make it ZL normalized plus J tangent B D1, and then 1 plus J ZL normalized tangent of B D1. And then I can also normalize ZL. And ZL has been given to me to be 100 ohms, so divided by 50 is just 2. So it makes the numbers simpler, smaller. And then I need to find this, ZL CC prime normalized will be nothing else but a parallel combination of ZS normalized with Z in CC prime normalized, which is that means 1 over ZL CC prime will be 1 over ZS plus 1 over Z in CC prime normalized, which means that ZL CC prime normalized will be Z sub S normalized times Z sub in CC prime normalized divided by the sum. Okay, and then I have which formulas now to consider? I have this one, has an unknown in there because I don't know D sub S. I have this one that has an unknown there. And I have this one. So if I put everything together, I'm going to have the following. 2 plus J tangent B D1 over 1 plus J2 tangent B D1, okay, times, that is your Z in CC prime, times Z sub S, which is J tangent B ds, okay, it should be equal. Well, let me, before I divide, I don't want to divide yet. And then one over J tangent B ds plus 2 plus J tangent B D1 over 1 plus J2 tangent B D1. Okay, and that should be, or let me put it this way, equal to ZLCC prime. But then, how much should that be? Z sub L CC prime, we said, for us to have a perfect match, meaning the gamma at CC prime should be 0. We need to have at ZL of CC prime to be 50, or the normalized of this to be 1. To be 1. Okay. With this one, that implies that this should be equal, since everything is normalized, to 1. Or it should be the following, if I do a little bit of math. Times J tangent BDS should be equal to J tangent BDS 1 plus J2 tangent BD1 plus 2 plus J tangent BD1. So practically I take the denominator here. I take this one to the other side, multiply with 1. So it's here. And then I also multiply this, the denominator, by this, and then add to the numerator. And then I have, therefore, the denominator here, and I have the same denominator here. And then I cancel the denominators. So practically, this one up here equals this multiplied by that plus this here. And this expression eventually gives you 2 simple equations. Then you can solve, you will see in my solutions, but it gives you the following 2 equations, because you have a complex number equal to another complex number. So the real and the imaginary parts have to be equal, which means real parts have to be equal and imaginary parts have to be equal. And that implies the following 2 equations from this one. Implies that tangent beta D1 times cotangent beta DS equals 1. That's one equation we find. And another is the 2 cotangent beta DS equals to tangent beta D1. These are the 2 equations we find. And from these 2, we find that cotangent of beta DS has to be 1 over 2. And from there, we find that cotangent beta ds is 1 over square root of 2. 1, this is 1. And then we find from here the tangent beta d1 is square root of 2. But this also, the top one gives us tangent of beta ds is square root of 2. equal. So what we find from finally this one and this one is tangent beta d1 equals tangent beta ds equals square root of 2, which makes d1 equals ds equals 0.152 lambda. And why is that? Because beta is 2 pi over lambda, if you remember. So this is how you solve this problem. So practically, in this solution, which is kind of extensive, but I wanted to do it for you here, so you see, we'll do more on Wednesday. We found that if D1 is 0.152 of lambda, and ds is 1.152 of lambda, then the reflection coefficient here is going to be 0, and therefore the input impedance here is going to be 50, which is going to give us the optimum transfer of power from the source to the load. Okay. Please look at this. I know it's the end of our hour, but look at this. And on Wednesday, if you have any questions about this, we will start with your questions about this problem. And we are going to solve another similar one. So can you show the final solution? Just a second, let me see. The final solution real quick. All of my notes are on, and better written even, but I will show it to you. There, oops. Is that the one you're talking about? This is the final solution. And if you go on the web right now on eCampus, you will see everything that I covered today is written well and clearly, and it is in 2 documents. The one document has the definitions and the open and short stubs and the impedances, and the other document has the problem. So everything is in there. Please read those 2. And also I will, I have an exercise for you today. I will turn it on after the class and I will keep it on until 6. And on Wednesday, we'll do 2 things. I've noticed that there are some difficulties with some concepts from the exercises. So we'll talk about those on Wednesday, and then we will also talk about the problem. Yes, about the recorded lectures, I have all of them. I don't make them available immediately because I think the students will not come to the lecture in the morning if I do that. However, I have them available and I will place them on the web, each one at a time. I need to do the first one and I will do it today, and then I will place the other ones. But please participate in the lecture because you have the opportunity to ask me real-time questions if you want. I did not see anybody raising their hand today. If you did and I did not see it, let me know. But I will encourage you to do that. Thank you. We'll see you on Wednesday.